Hi everyone. Today I want to share with you a video that I just recorded for Haskell Implementors Workshop. This was a workshop that took place on Sunday, August 22nd, and I gave a talk about generalization. I think it'll be interesting to this audience as well. So with that, we will roll the video. Thanks. Bye. Hi everyone. Thanks so much for tuning in to this talk about generalization. We're going to be going through some code during the talk. All that code is going to be available from this folder here, so you can go ahead and download that, or not. You won't need to download that to be able to follow along with the talk. So what do I mean here about generalization? This is really about figuring out a type for a Haskell definition that has no type signature. Because the idea there is that if I say something like id x equals x, but give no type signature, we have to realize, oh, that works for any x, any x of any type. That process is called generalization, and it's a major part of the description of the Hindley-Milner type inference system. But it turns out there's a lot of details to it. So this talk is all about walking us through those details so that we can understand a little bit about how this works under the hood. The talk is going to be mostly example based, but with a little bit of reference to code. Okay, let's dive in. So here is how we do generalization. This is all done really in this function decide quantification inside of GHC. So if you want, you can check that out. But I've sort of abstracted over that and I'm really going to try to explain all of the different steps here today. The first step in figuring out what the type of a let binding should be is to generate constraints. So this means to examine the code on the right-hand side of the let binding and seeing what it says. So as a quick example, if we have some definition that maybe looks like f x y equals x comma y, so let me just make that clear. Okay, so if we have a definition like this, well, the constraint that will generate is, well, we know that x has to equal y because they're both elements of this same list. So that's generating constraints. Then the next step here is to simplify constraints. So here, if say we had x, y, and then maybe here, oh, this isn't a tuple, perhaps, not capital, show x. If we have something like this, well, now we additionally have a show constraint. And so simplify constraints here goes through and tries to simplify all these constraints. If we have an equality constraint, maybe it sets the type of x to equal to the type of y. Sort of depends on the details here. We're not really going to be talking very much about steps 1 and 2 in this talk. What we're really focused on is step 3 and thereafter. So once we've simplified the constraints, that means that we have several facts that we know about the types in play here. And then we have to figure out, okay, given these facts, how can we figure out the type of the let definition? So the first step here is to determine ungeneralizable variables. So we'll see an example of that. And by the way, I'm going to be returning to this list a bunch of times throughout the talk. So this is not only the list of things that we do when we generalize, but it's also the outline for the talk. So let's keep scrolling down. So now we start to see real code. And we're going to start with something simple, x equals 5. So if I load x equals 5, so you see down here that there's a bunch of stuff going on. That's because I've enabled some flags. We'll get back to that in a minute, but we'll see some extra gunk printed out every time I load. But right now, I want to look at what the type of x is. X is of type integer. So already that's a bit funny, right? Because x equals 5, what that should say is that it's going to produce that x is some type A0. Following GHC convention, I'm going to take unification variables and put a little number after them. So that means that I don't know what the type A is yet. But x is going to have some type A0, and we also have a constraint num A0. But none of that says integer. So the first step that I said above is we need to determine the ungeneralizable variables. So this is actually 3b, because in the definition x equals 5, I wanted to start with something simple, here the monomorphism restriction applies. right? The monomorphism restriction applies anytime we have a definition that does not look like a function. And by does not look like a function, I mean it has no arguments before the equal sign. Then what that means is that we can't have a constraint inferred as part of the type. So I could write num a arrow a here, and that would compile. We get OK at the bottom here. But if I'm inferring a type, then the monomorphism restriction means I can't infer any constraint here. And so that means that this A0 mentioned in a constraint is ungeneralizable. And indeed, we won't generalize it. And so what GHC will do is at the very end, it defaults. And so we can see this if I enable set type defaults and then load, we get a warning saying that we've defaulted this constraint to have type integer. That's actually kind of a poor error message. Maybe we'll return to that at some point. But here we get a default type for x, and we'll infer the type integer. Okay, let's move on to the next example. So here's our next example, warble. So the question isn't what is the type of warble, but what is the type of verb? And so that's why down here we're getting this extra gunk. So what I've done previously in my GHCI session, but I'll do again just so everyone can see it, is I've set dedump tc, which outputs the result of type checking, as well as print type checker elaboration, which means it prints out some stuff that normally would be suppressed, but it's actually the type checker elaboration that we're interested in here. If I do that and I load this, then we get to see the types inferred for local bindings like verb, right? I can't do :i on verb because it's this local binding. So let's think about what's happening here, and then we can understand how generalization is getting affected. So here we're going to have x has type A0. We don't know anything about A0. Then when we get down into verb, x is still in scope, but now we have y. Y is going to have type B0. And then we get a constraint, A0 must equal B0. That's because they're used on both sides of a plus, and plus requires the same type on both sides. We're also going to get num. Well, we're going to get a num later on. Not yet, because we're still trying to define verb, and we haven't really looked at this part over here yet. So at this point, what we wonder, okay, what are we going to generalize over? So if A0 equals B0, then I'm actually going to go one step further, and during my simplification, we're actually going to choose B0 equals A0. So that means that the type of y and the type of x should be the same thing. The type of verb is going to be something like A0 to A0, because the type returned on the right is the same thing as the type taken on the left. But now, am I going to quantify over A0? Is verb going to have type for all A0, dot A0 arrow A0? Well, no, it can't, and that's because this x comes from an outer scope. I can't generalize verb over that type. And so this is really 3a. This A0 comes from an outer scope, so we can't generalize over it. So down here, when I infer the type of verb, we see here, where is it? That verb has type P to P. But there's no for all here. The for all would be printed if it were there. And out here, the overall type for verbal is also going to be P arrow P, but with this num constraint. Okay, so that's another restriction. That's this part of generalization where we decide what we can't generalize over. Okay, so that's actually, we might as well keep those comments in. And let's comment this out so it doesn't clutter the output. Now let's move on to our next example. This one's a little bit more involved. So here we have a type family F and inject, which just takes something of type A and turns it to have something of type FA. Then here I'm actually going to give F a type signature, going A arrow unit, and Fx equals unit. So that's pretty simple. But here I'm going to have this GY is a list of inject X, inject Y. And now let's see what happens when I try to compile this. So we get this error. So now when we try to understand this, let's think about what's going on as we're trying to figure out, infer, or generalize the type of G. So I've commented out a type signature. It turns out that signature will work, but that's not what GHC is about to infer. So don't get fooled by it quite yet. Instead, we're going to see that X has type A. We know that from the type signature for F. Y, well, a priori, we don't know what type A has, so I'm going to give it type B0. We'll figure out what it's going to be. And then G is going to have type B0 to, oh, well, there's this list, and that means that these two have to have the same type. So we're going to get a constraint that F of A equals F of B0. And then G is going to be, well, B0, I guess, to list of FA. But now the question is, do we generalize B0? And so in my rules that I have up above here, variables from an outer scope, we don't generalize. That's like A in this case. The monomorphism restriction doesn't apply. But then it's variables related by equality constraints to the above. So that means that, where are we? Here we are. That down here, this B0 is related to A by an equality constraint. And so it means we actually won't generalize this B0. And in the end, we get a type error because we don't know what B0 should be. Here, the type error is calling it A0. But in the end, we just have no way of knowing what it is. It's just ambiguous. And so our program is rejected. And no, it doesn't say to enable ambiguous types. This isn't about inferring an ambiguous type. It's about a unification variable for which we have no information. And so it means that A0 is ambiguous here. If I give this type signature, then everything is okay. And because now I'm explicitly saying I do want to quantify over B. It's not one of these ungeneralizable variables. Okay, let's move on. So that's the first step. The first step is figuring out the ungeneralizable variables. The next step is to do defaulting. So we want to default levity, representation, and multiplicity variables, and then sometimes kind variables. So the good example of that is here. So IDI here, if I compile and I look, what is the type of IDI? Well, it's for all P, P arrow P. And now GHC won't print it out, but P really just has kind type here. But there are other good types for IDI. Maybe IDI doesn't work over lifted types. Maybe it works over unlifted types. This is a perfectly good type for IDI. If I try to compile, I think I'm going to get things that are out of scope. So let's fix that quickly. Oh, and now we need data kinds. And now it works. But that's not the type that was inferred for IDI. And that's because when I have a type variable that I don't know what its kind is or what its representation is really, I'm going to default that. So that's one of these steps to generalization, right? If I don't write that type signature, then indeed I get this with just kind type. If we turn off polykinds, right? Polykinds is enabled by default in GHC 9.2, which is what I'm working with here. If I turn off polykinds, then polymorphic types or rather kind variables get defaulted to star. So let's look here. For this example to work, I'm going to need to disable the monomorphism restriction. So let's turn off no monomorphism restriction. Now this catid, it gets this inferred type involving K. If I turn off polykinds, then we see that it gets defaulted to star. So this is the action that happens in step 4, defaulting. Next, we're going to choose the quantified variables. So these are variables that are mentioned in the body of the inferred type or any variables that are related to those in a constraint. So let's see some examples of this. So we'll comment this out. So here are some examples. If I compile this, we can look at printed. Oh, we get some defaulting here. Let's turn, oh, that's down here. Well, let's not worry about that. So here, if I look at show 5, well, what's the inferred type of show 5? It's got to be string. And so where is printed? Printed indeed has type string here. But if we look at the definition, it's actually specializing this to integer. We're choosing that 5 is going to be integer and not, say, double. And the reason for this is that in my inferred type, I get that printed has type string, but then there's also this num a0 constraint, and a show a0 constraint also. And I don't really know what to do with those constraints. I'm not going to quantify over the variable a0 because it's not mentioned in the head of the type string. And so I don't quantify over a0, and instead I have to use defaulting in order to choose what 5 should be. Of course, this matters, right? If I chose that 5 had type double, printed would be 5.0 instead of 5. So this defaulting can affect runtime behavior. We have a similar thing that happens here in measured. In measured, the inferred type is int, which doesn't mention the type of the element type in my list here. So if we look at this here, length gets specialized to any, which is the type that GHC uses when it really just doesn't matter, right? So here I get that measured has type int, and there's actually no further constraints. So if we have a variable that is totally unconstrained, it just gets defaulted to any, which should never really appear in any error messages or really matter at all. Unlike up here, where it does matter, it changes the runtime behavior. Here, the choice of element does not. So up here, let's see, I said that we were going to choose quantified variables, something in the body of the inferred type, or related to those in a constraint. So down here, well, let's look at this. We have two examples here. So we have frob and zerp. And then I have a class frobzerp, which just does both of them. But it's not really related directly to frob or to zerp. So here, if I look at frozu, let's compile frozu. So frozu gets this inferred type. And what's happening here is that A, the type of X here, well, that's mentioned in the type of frozu. Frozu is going to be of type A arrow unit. But what type should I use for 5? Again, 5 is an overloaded number. It could really have any type. And here, because B, the type of 5, because that's related to A in terms of this frobzerp constraint, we're going to quantify over B, even though it doesn't appear over here. By contrast, if I try to compile fro underscore zoo, I get an error saying that we can't deduce zerp a0 or num a0. Here a0 is the type of this 5, and we can't solve these constraints because I don't have a default that has a zerp instance. But I don't quantify over the type, and that's because here the constraints that I get are just frob of, well, I'll call the type of x b0, frob of b0, zerp of a0, and they're not related. Up here, I get frobzerp of b0, a0, and they are related, and so we do quantify over both. Okay, let's move on after this example. So let's see what's next. So then we have to actually choose the quantified constraints. Right, now that I know what variables I'm quantifying over, then maybe I want to choose the actual constraints that mention the quantified variables. So we have yet another example to look at, and that's, oh, no we don't. I think actually it's this example. Again, this x equals 5. So if we look at this, but now we're going to re-enable the monomorphism restriction. Well, if I've decided not to quantify over a0, I had better not quantify over num a0 either. Right? It would be very strange to have the type of x be x is num integer, arrow integer, even though that's actually valid, but we don't want to do that. So we're not going to quantify over the num constraint because it doesn't mention any variable that we're quantifying over. So that's part of this A here. But then we also have various special cases. So implicit parameters are always quantified over. Has call stack is never quantified over. There's a few other cases handled here. The last step is that we remove redundant superclasses. So we can see that in my final example, check refl. So here, if I try to compile check refl, then, and I look at its type, I see that even though it uses both an equality method and an ORD method, an eq method and an ORD method, my inferred type only says ORD A, because there's another process which looks at ORD A and eq A and says, oh, well, if I'm quantifying over both ORD A and eq A, that's a bit silly. Let's just quantify over ORD A because that implies eq A. And so that's a small simplification that we would get on the type of check refl. So that's really what's going on. It's this whole sequence of steps, and there's a lot of details here. So I've skipped over a bunch, including a big complication is partial type signatures, where I want to perform all of this, but it's actually guided by some information given by the user. I've also skipped over mutual recursion. If I have multiple different definitions, some of which have type signatures and some of which don't, there's all kinds of interactions that can happen that I didn't get into today. Implicit parameters have some strange effects, as do functional dependencies. There's something called naughty quantification, which is when I have a type variable whose kind mentions a kind variable, and I can't quantify the kind variable, but it looks like I want to quantify the type variable. Oh, no, I got that other way around. When I want to quantify the type variable, but I can't quantify the kind variable, there's no way of doing that in a good scoped way, so that's called naughty quantification within GHC. And then, of course, there's lots of implementation details. So we're not really looking at GHC's code, but just sort of extrapolating out the algorithm here. So upshot is now we have a little bit more perspective in how quantification works and the various steps that are involved when we do quantification in a language like Haskell that has more than just type variables. When we have constraints, it's a little bit harder. Thanks for listening. Bye.